Okay, welcome to another session of Introduction to Photonics. So far we have been talking about light sources. We started talking about spontaneous emission and stimulated emission of light leading to optical amplifiers and lasers. And so far most of the examples that we have taken is for dilute gas of atoms. So typically you talk about an atom, you say okay, you have an isolated atom which may have different orbitals, and so you have a valence electrons in one of the outermost orbitals, and from there it can get excited to higher energy levels, and we were talking about from the valence orbital to some other energy levels, transition between other energy levels. Now what we will start looking at is semiconductor material, and when we talk about semiconductor material, the model changes a little bit. You are starting to talk about electronic charges moving in the semiconductor material, which are potentially leaving behind holes, that is absence of charges in certain regions. And now we are going to start talking about recombination of these charges, electrons with holes, which may actually give rise to light emission. Okay. And of course, it can also do light detection, in which process you have light coming in incident on this material, which produces electron and hole pairs. Okay. So, we will look at some of those principles. Now, the primary difference is here we are considering a system of atoms. Let us say they are all periodically arranged. Okay. Now, each of these atoms actually constitutes what is called a potential well. Okay. So, you would have a potential well associated with each of these atoms. So, why do we have this potential well? Essentially what we are saying is this atom at the center of that is going to have these positive charges, and then you have these orbitals for these electrons which are quantized in nature. So, they occupy different levels, and it is going to take a lot of work to so there is some attractive forces between the positively charged nucleus and these electrons that are orbiting, and that constitutes a certain potential, right. So, we are going to have these potential wells, and the important property of these potential wells is when we talk about existing of an electron, right. The electron is going to have different orbitals. So, you can basically say it is going to occupy different orbitals that can be represented like this, and then of course, you can have higher orbitals also. But the unique thing is when we talk about the wave function related to an electron. So, what do I mean by the wave function? I am talking about the probability of existence of an electron. Okay. That would potentially be very high within that potential well. So, because it is going to be bound to an atom, right. But it can also have a finite potential of existing in a nearby potential well as well. Okay. So what we are saying is when these atoms are close to each other and they are periodically arranged, your valence electron, which is typically bound to an atom, you would say is okay. If it is isolated, you can say for certainty that it's going to be bound to that atom itself, right? But when you have a collection of atoms like this, there is a finite probability that it may exist in a neighboring potential well as well. So what we are now saying is all these wave functions are going to have these tails that are existing, that are extending to these nearby potential wells as well. So in other words, all these potential wells, all these atoms are coupled with respect to each other. Okay, so now we are starting to talk about electrons and transport of electrons, which is governed by what is called the Schrödinger wave equation, right? That basically talks about the energy of an electron and then the movement of electron within this material. And that is essentially saying that, okay, when all these potential wells are coupled with respect to each other, okay, then you have a slightly different transport mechanism. And to give you an idea of this, what we can say is, when we talk about valence orbitals, those can exist up to, let us say, this level. So let us say this is EV, okay. And then what we will see is it is either bound to these potential wells or bound to these atoms, or it is free to move around the lattice. If you give it some energy, some external energy, it can actually unbind itself from that atom and then it is free to move around that lattice. And that is defined by this energy that you call as EC, that is the conduction band energy. And then it can, in this region there is, it's called the conduction band. So beyond that energy, it is free to move around the lattice. Okay. So there are two distinct states that these electrons can have. One is either they are bound to one of these potential wells or collection of these potential wells, right, which is called the valence band. Okay. And then with a certain level of energy, it can unbind itself and then it is free to move around the lattice, and that is what you call as the conduction band. Okay. Is that clear? So what it also tells is that when you work out the Schrödinger wave equation for this sort of a model, this model is actually what is called the Kronig-Penny model. So it's clearly named after a couple of scientists by name Kronig and Penny, who came up with this brilliant idea of modeling this collection of atoms and modeling how the electron transport happens in this collection of atoms. So with this model, you solve Schrödinger wave equation. What you find is there is actually a forbidden gap. So the electrons cannot exist within this energy level. It can either be bound to one of these potential wells, in which case, you know, it's in the valence band, or it's completely unbound and it's free to move around the lattice, which is the conduction band, and then there is a certain energy gap between the two, which is where the existence of electron is not possible in that material. You understand that? It's digital, it's either bound or unbound, and then in between there is a gap, okay. And this is actually called the band gap of the semiconductor, and that is actually a very unique characteristic of the semiconductor, okay. So it's essentially got this forbidden gap, okay. And so you ask the question, why is it called a semiconductor? Essentially, this band gap energy, which you can denote as Eg in a semiconductor is typically much larger than kBt. What is kBt? Thermal energy, right? For a given temperature, what is the energy that we have? So if Eg is much greater than kBt, what can you say about an electron existing in the conduction band? You don't expect you don't expect to see any electron in the conduction band, because your your thermal energy is not enough to take an electron from the valence band to the conduction band, okay. So it essentially acts like an insulator at 0 degree Kelvin, but as you elevate that temperature, you have a finite probability of an electron existing in the conduction band, in which case it starts conducting, right, and then it becomes what is called a semiconductor. Under certain conditions it acts like an insulator, certain other conditions it acts like a conductor, okay. So it's in between a conductor and an insulator. So clearly you can characterize it as an insulator as long as T equal to 0, or maybe even for small values of T, maybe even room temperature, but as you elevate the temperature it becomes a conductor, okay. And of course a conductor is one in this model where you can characterize it as the conduction band and the valence band are overlapping. So even at room temperature there is a finite density of electrons in the conduction band, so these are free electrons, they are free to move around. So you take one of these wires, you have a lot of free electrons, so it does not take much potential to move them around, right, you can conduct current. Whereas the other extreme is the insulator, where the band gap energy is so large that even when we try to apply a potential between them, it does not conduct. A dielectric is a good example in general, right? Any questions about this? Okay, so when you solve this Schrodinger wave equation without going into a whole lot of detail, what you also see is something like this. Sorry, I already drew this, so I'm just going to, because I'm going to keep repeating this, right. So you have what is called, this is energy and this is momentum, represented as K, represented as E, right. So you have, when you solve Schrodinger wave equation, you get an expression for the energy of an electron, okay, which is actually a function of the momentum, okay. Specifically, what we will see is if we say this corresponds to EC and this corresponds to EV. The topmost energy level in the valence band we are defining as EV, and that bottommost energy level in the conduction band we are defining as EC. Then we will see that the energy of an electron in the conduction band has to satisfy this expression. I am just giving you a solution of the Schrodinger wave equation. I am not solving it here because in the interest of time, but the solution would work out to be something like this, right. And over here the solution is EV minus h square corresponds to the h corresponds to the Planck's constant, and h cross corresponds to h over 2 pi, right, and k is the momentum. And then this specific quantity which we are calling as mc and mv, okay, that corresponds to the mass of an electron in the conduction band, effective mass of an electron in the conduction band, effective mass of electron in the valence band. And what we will see is the curvature. So essentially what this equations represents is a equation of what? If it's quadratic like that, it's an equation of parabola, right. So you're talking about two parabolas, but what we are seeing is one is actually not so curved, it's relatively flat with respect to the other, right. The valence band is typically relatively flat with respect to the conduction band, and that is because of the concept that the effective mass of an electron in the valence band is larger compared to the effective mass of an electron in the conduction band. Maybe you can physically understand it from this picture. In the conduction band it's free to move, so the effective mass is like low, right, whereas in the valence band it has all these potential wells that are like speed breakers, if you may, right, in a very crude sense, right, and so the effective mass is actually reduced. So because I mean the effective mass is larger in this case, and the mobility is reduced, and because of that you have a flatter EK curve. Yeah, you have a question? No. So the question is, are we talking about particle movement greater than the speed of light? No. We are certainly talking about particles which have a certain mass, right. The speed of light is where you get these photons which have zero rest mass that are propagating in space. So that is the highest speed that you can achieve, but because of the fact that they have a finite mass, they cannot certainly achieve that speed, right. So we are certainly talking about in terms of speed of motion in this material, it's much lesser than the speed of light. So it's not like physically the mass is different, right. What we are saying in the valence band is that it actually feels a certain field, certain attractive force towards the nucleus that effectively reduces the speed, reduces the mobility, okay. So effectively we say the mass is larger. It's not physically any different in terms of the mass carries. Okay. So now we are gonna just, while we stay in this thing, when we are talking about atomic systems, right, dilute atomic systems. We were talking about transitions between these energy levels. Now, when we are talking about semiconductors, we are going to start talking about transition between the conduction band and valence band. Having said that, I will also say that there is research going on in intra-band transitions as well. Okay, so people are starting to, within a semiconductor, can you have transition between one part of the valence band to the other part of the valence band? For the simple reason that when you look at these sort of transitions, those are much lower in energy, right? And much lower in energy will correspond to, in terms of wavelength, what does it correspond to? Very long wavelengths, right? So now people are requiring mid-infrared light sources. One example of where mid-infrared light sources will be useful is when you consider absorption of the fundamental absorption tones of different gases, okay, or different material in general, different elements. You find that the fundamental absorption tone is actually in the mid-infrared region, 3 to 5 micron region, right. So, if you go to that region, you will find that the absorption is very, very high compared to the absorption that you may have in the near infrared or visible region, okay. So, if you want to pick up trace levels of these elements, you want to detect them with very high sensitivity, you want to actually use mid-infrared light sources for doing absorption spectroscopy. Remember we talked about absorption spectroscopy a few weeks ago when we were talking about interaction of a photon with an atom. We were saying that based on that absorption you can detect different elements, absorption signatures. So that detection is much more efficient if you go to mid-infrared light sources, and to do that people are exploring intra-band transitions, but for all the discussion that we are going to have as far as this course is concerned, we are going to be focusing on inter-band transitions, transitions between the conduction band and the valence band. I will come to that. So, the question is, there are certain things called radiative transitions and non-radiative transitions. So, how do those happen in these things, in the semiconductor material? I'll come and explain that a little more detail, but from our previous discussion that non-radiative transitions are more likely if your energy difference between the different levels is very small. What do you mean by very small? It's comparable to KBT, right? Then you have non-radiative transitions possible. But if you have a pure band gap, a band gap with energy of 1 eV, your energy corresponding to thermal light at thermal energy at room temperature corresponds to about 25 milli electron volt, right. So, if energy is 1 eV, then you are more likely to have radiative transitions, when we consider jumping between conduction band and valence band. Okay. If you have a case where the conduction band bottom, right, the lowest energy level at the conduction band aligning with the top of the valence band, you call that as a direct band gap semiconductor, because the transitions can be just direct. So, if there is something called direct band gap, you realize that there's got to be something else called indirect band gap, and clearly with indirect band gap what you can say is your valence band maximum and your conduction band minimum, they are not happening at the same value of k. Okay. So, so you have EC here and you have EV here. So, even in this case the band gap energy is still this corresponds to EG, but you do not have a direct transition between your conduction band and the valence band. So, in this case when you have a transition, energy is conserved as well as momentum is conserved, right. For any of these things to happen, any of these events to happen, both energy has to be conserved, momentum has to be conserved, okay. And that is straightforward in a direct band gap semiconductor, but it is not so straightforward in an indirect band gap semiconductor. Your transitions would have to satisfy energy conservation, which can be basically saying that okay, transition across EG, but also it has to satisfy this momentum gap delta k, right. So, it has to involve some other quantity which satisfies that momentum gap as well. So these transitions are relatively little more involved or little more complex, okay. So we will come back and see what is the consequence of that. Just to give you an idea, direct band gap semiconductor, one example of that is gallium arsenide. It is a common example that we will keep using, and indirect band gap semiconductor, a very common example is silicon, okay. So it does have, I should just complete this picture, it does have, it may have an edgy structure like this. It is just that the bottommost part of the conduction band is not aligned with the topmost part of the valence band, okay. So that is one aspect that we need to keep in mind. There are a couple of other things that we need to keep in mind as well. The other aspect is there is a certain so when you actually once again solve the Schrodinger wave equation and look at these energy levels, what we will find is you find that the density of energy levels is actually relatively low near the band gap, and the density increases when you go further away from the band gap. So, so if we were to represent the density, so this is EC and this is EV, what you will find is the density, let us say I'm representing as rho C in the conduction band and it is rho V in the valence band. You will have a certain dependence like this, and this is this density, what we will see is proportional to E minus EC to the power of half, and here this is proportional to EV minus E to the power of half, okay. So the what we are saying is density of states in both valence and conduction bands is higher as we move away from the band gap, right. So, density of states in valence and conduction band is higher as we move away from the band gap energy. Okay. So, that is with the density of states, but there is another important aspect that needs to be considered, okay, and that corresponds to the probability of existence of an electron in any of these states. So, question is, I want to look at what is the probability of an electron existing in this particular energy level, right. So, how do I find that? Okay. So, that has been once again investigated previously, and people have come up with an empirical relationship for this. So, probability of occupancy, talking about an electron occupying a particular energy level, that is, in this case it's actually given by what is called the Fermi-Dirac distribution. Okay. So, what the Fermi-Dirac distribution says is f of E is going to be given by 1 over 1 plus exponential of E minus EF over kBT. Okay. So, in this what we are seeing is that we are introducing a new quantity that is called EF. So, what does that quantity mean? Now, we will just put this in perspective once again. So, according to this expression, if we plot, let us say, the this axis, we are looking at f of E, right. The probability of an electron occupying one of these energy levels as a function of E, right. E is increasing in that direction. Okay. So, what this says is, if you consider, so this is going from 0 to let us say 1. If you consider when T equal to 0 degree Kelvin, okay, you get something like this. So, this would be, use a different color here, this will be EF, and then this is basically saying so what this means is no probability of electron existing in these regions, okay. Whereas you have a probability of 1, right. So, you can say for sure that the electron is going to be existing in one of these valence energy levels. Okay. So, that is at T equal to 0 degree Kelvin, but if you consider T greater than 0 degree Kelvin, you draw the same expression and this expression now comes into effect. Now, you say this is still your EF. So, this is going from 0 to 1, we are looking at f of E, and this is about 0.5, so that is about this point. If you plot that expression, it's going to be something like this. So, what it says is, in this case there is a finite probability of electron existing in this conduction band. So, now just to give you a perspective, so now we are saying this is your EC and this is your EV, and there is also a finite probability that in this case over here, finite probability that electron does not exist in this valence band. Okay. And if there is actually an absence of an electron in semiconductor physics, we call that as a hole. Okay. So, this actually corresponds to the fact that you have a finite probability of holes in the valence band. Okay. So, what we are typically interested in is this quantity. We are interested in what is the concentration of electrons in the conduction band and the concentration of holes in the valence band. Okay. So, that concentration is essentially going to be, if you are looking at the total, so well, first of all that concentration is going to be equal to the density of states rho c of E multiplied by f of E, right. So, the density of states multiplied by f of E would give you the distribution of electrons in the conduction band, and similarly rho V, that is the density of states in the valence band multiplied by what? 1 minus f of E, because we are talking about the existence of a hole. So, the existence of a hole is when you do not have an electron in those energy levels, right. So, if you want to look at the total, this is the concentration, this is the density that is distributed across the different energy levels, and if you want to look at the total electron density in the conduction band, what you have to do? You have to integrate over this. So, in this case the integration will happen from EC to infinity, right. You over all values of dE, if you do that integration, you get the total density of electrons, and similarly the total density of holes in the valence band is given by integral over dE. What are the limits? Minus infinity to EV. Okay. So, what we find in this case is if you look at, for example, if you look at this is your EC and this is your EV. If you look at the distribution of electrons, it is going to be something like this. Right, and the distribution of holes is going to be something like this. So, so this is basically N of E and this is P of E. So, what are we seeing? What do we see in this structure? What we are seeing first of all in N of E is that you have a higher probability of finding an electron near the band gap, right, but there the density of states is very low, okay. But as you move away from the band gap, your density of states is higher, but according to the Fermi-Dirac distribution, that probability of existence is lower. So, that is what is, so the N of E will actually trail off as you go to higher energy levels, and similarly with P of E. But what we gather from all of this, if you look at charge neutrality, what you find there is the total number density of electrons is equal to the total number density of holes is equal to this quantity which we can write as Ni. So, this is what is called an intrinsic semiconductor. Intrinsic semiconductor is a semiconductor without any doping. Let us say silicon, for example, without any doping, or gallium arsenide without doping, will have equal number of electrons as there are holes in the system, and so N equal to P equal to Ni. Okay. Now, interesting things happen when you have dopants added to this system. Okay. So, you have what is called extrinsic. Yes, one second. Yeah, there is a question somewhere. Yeah. Yeah, I mean, you can bind it to a specific level, but I mean, this is like all possible levels. So, you just say minus infinity, but in reality you do not see much happening beyond a certain level. Yes. No, it is not minus infinity. So, there is no meaning of minus infinity in this case, but yeah, mathematically you are just trying to do that. Physically, you don't attach a meaning to that. Yes. Yeah. Well, yeah. So, it cannot have infinite energy. That is basically what he is talking about. So, you cannot have infinite energy at the lower bound or the upper bound, but mathematically you are just trying to account for all possible energy levels, right. So, yeah, that is not physically possible. But interesting things happen when you have doped semiconductors, and as far as doped semiconductors go, suppose you could have N-type or P-type semiconductors. N-type is where you have let us say an example of that is silicon, which is actually quadrivalent semiconductor. It has 4 valence electrons doped with let us say a pentavalent element like phosphorus, right. So, silicon doped with phosphorus can give you some interesting things. When what we are talking about is this is, let us say, for simplicity I will just draw it as a flat line, EC and EV. You have phosphorus. When you dope it with phosphorus, phosphorus actually occupies an energy level, let us call that ED, somewhere over here, such that even at room temperature, since it is pentavalent, it has got one extra electron to give, right. So, even at room temperature you have electrons that are going into the conduction band, right. And similarly, if you talk about P-type semiconductors, silicon doped with a trivalent element like aluminum, right. And in this case the aluminum is going to occupy a state over here, and it is such that you can have these electrons are accepted by aluminum, and in this case what you have, what you are leaving behind is holes. In this case what you have is extra electrons over here, okay, and that actually changes the electron and hole concentration. So, you have basically when you are looking at the electron concentration, it is going to be much larger like this, whereas your hole concentration is still much smaller. Whereas here your electron concentration is like this, but your hole concentration is much larger. So, this is N of E and that is P of E, this is P of E and N of E. And to represent that, to explain this part from a Fermi-Dirac perspective, what you can essentially say is that your Fermi energy in this case would have shifted over here, right. It shifted from the Fermi energy in an intrinsic semiconductor is EC plus EV divided by 2. But now with an extrinsic semiconductor, the Fermi energy moves up or down depending upon the kind of dopant that you have. So, here the Fermi energy is going to be like this, okay. So, then you have basically a larger probability of finding an electron in the conduction band in the N-type semiconductor, and a larger probability of finding holes in the valence band as far as the P-type semiconductor is concerned, okay. So, here you have in the N-type you have excess electrons, and here you have excess holes, okay. Now, interesting things happen when you have these excess electrons and holes, and before we talk about that, Now, we can also say something else when we are looking at this picture, right. So, when we look at this picture, what are we saying? There is, from a perspective of light absorption and emission, you can say that you can have light with h nu come in, a photon with energy h nu come in, such that h nu is, if it is greater than the band gap energy, then it can actually be absorbed in this material, and whenever that absorption event happens, it leaves behind a hole in the valence band, and it creates a electron in the conduction band, right. So, that can happen. Maybe I can just represent this in a separate picture over here. So, let us say you have h nu is greater than Eg, then you have this transition happening, leaving behind a hole here and producing an electron there, right. So, this is actually absorption process in a semiconductor, whereas now if you say you have an electron over here and a hole over here, it actually spends some time and then it can actually recombine with the hole, which can emit a photon. So, that is what we call as spontaneous emission. And finally, you have also this possibility that if you have an electron over here and a hole over here and a photon comes around corresponding to the energy difference between where the electron is sitting and where the hole is sitting, you can stimulate a transition, and in this case you have stimulated emission, which essentially means that you could get optical amplification, and then with feedback you can actually make a laser. Okay. So, we are out of time, so let us stop over here, but these are the things that we are going to be talking about. We are going to be talking about light emitting sources, which are based on spontaneous emission and stimulated emission of light, and we are going to also look at light detectors, which are based on absorption of light. Okay. So, that we will continue in the next lecture. Thank you.